Welcome to Chapter 3 for the online video lecture series of Intermediate Algebra at Wayland Baptist University. I'm Dr. Scott Franklin. I'll be leading these lectures. In Chapter 3, we're going to start looking at a type of mathematical object called a system. A system is going to be multiple equations considered as a group. So we're going to look at systems of linear equations. Now, we've done linear equations so far, and in fact, when we saw linear equations in one variable, those are the simplest types of equations that we have learned how to solve. Now we're going to have systems of equations where we have multiple equations and usually multiple variables involved. And so whenever a solution is to be found for a system, we're going to try to find something that satisfies all of the equations at the same time. And this becomes pretty useful in applications where we have more than one constraint on our relationships between the variables. There's not just one relationship, but there may be multiple relationships or multiple constraints on those variables that we need to use to answer questions and find that unknown or missing piece. To begin with, in section 3.1, we're going to look at systems of linear equations in two variables. We're going to consider what are called 2 by 2 systems, two equations with two unknowns. The essential concepts for section 3.1 include the following. We're going to determine whether or not an ordered pair is a solution to a system of linear equations, and we're going to then learn how to solve systems of linear equations by three different methods. We're going to first talk about solving by graphing, then solving by substitution, and then solving by what's called linear addition. Following that, we need to talk about what's the best way to solve. Since we're learning three techniques, obviously there's going to be different situations where one might be better than the other. So we're going to learn how to select the most efficient method for solving a system of linear equations. And lastly, we need to identify systems that don't have exactly one solution. There are other types of answers that we might get besides just a single answer to the system. So let us consider systems of equations. We are asked to determine whether an ordered pair is a solution to the system of linear equations. Now what that means is we want to check whether or not when I plug in 3, 2, that is 3 in for x and 2 in for y, into this system here, does it satisfy both equations simultaneously? That is, if I treat this as a group, does this ordered pair satisfy the first equation and the second equation? Does it make it true? So to check whether or not something's a solution, all you got to do is plug it in. So to do equation 1, we would simply plug in 3 for x and 2 for y. So negative 3 times 2 plus 6 times, let me do that right again. I'm plugging in 3 for x, so negative 3 times 3 plus 6 times 2. I'm just sticking in 3 here and 2 here. The question is, does that equal 10? If it does, then it satisfies the first equation. We'll then have to check the second equation. So plug this in, I get negative 3 times 3 gives me negative 9. If I plug in that plus 12, is that equal to 10? And I get negative 9 plus 12, and I get 3 equals 10, which is wrong, which means no, it is not. I don't even have to check the second equation now, because if it doesn't satisfy the first, then it can't satisfy both of them at the same time. Right? Now let's do the same thing on the next example. Let's plug in 3 for x and negative 4 for y into this system and see what we get. Alright, so negative 4, this is the first equation. Plugging in negative 4 for y equals, question mark, 6 times 3 minus 22. Okay, is negative 4 equal to 18 minus 22? And I get negative 4 equals negative 4. So that checks. Now, that doesn't mean it solves the system. All that means is it solves the first equation. Is it a solution to the second one? We also have to check. So 2 times 3 plus 6 times negative 4, is this equal to negative 18? 2 times 3 is 6, plus 6 times negative 4 is negative 24. 6 plus negative 24 is negative 18. That does equal negative 18. So yes, it is a solution. Okay, so that's how we check to see whether or not an ordered pair is a solution. Now our general goal is going to be, given a system like either one of these, can we find the solution if we don't know it ahead of time? There are three techniques that we're going to learn for solving systems of linear equations in two variables, and in particular we're going to look first at graphing, then at a method called substitution, then at a method called addition or linear addition. Okay, in different circumstances we'll want to use different techniques. They all have advantages and they all have a couple of disadvantages, so we'll have to decide later on which one's the best technique given a particular situation. Let's start off by talking about how we graph to solve a linear equation. Recall that if I have an equation in two variables and it's of the form ax plus by equals c, that graphs as a line, right? Now if I have two equations, that means I have two different lines. Now to solve the equation solve the system means to find any point that's on both lines at the same time. In other words, trying to find where they intersect. This would be the solution. That point right there where they intersect would be the solution to a system where these were the two lines, two equations. Okay? So to solve by graphing, what we do is we graph the first equation, then we graph the second equation on the same set of axes. If the lines representing two graphs intersect at a point, we determine the coordinates of this point, and that ordered pair is the solution to the system, and then we can check the solution in both equations. Okay, so graph them both. If they intersect, the intersection point is the solution to the system. So here we go. We have this problem where we're asked to solve it by graphing, so I'm going to graph each of these separately. So call this equation 1, call this equation 2. Let's graph them on the same graph using the technique that we learned from chapter 2, where we can graph using just the x and y intercepts. So for the first equation, x and y, I'm going to plug in 0 for y. That gives me 4x equals 4 because the y drops out. Divide both sides by 4, I get x equals 1. If I plug in 0 for x, I get y equals 4, right? Just because the 4x drops out. So I get this. So if I were to graph that on our Cartesian system, okay, then those 2 points are, let's see, right here we go, 1 and up 0. So there's my first point. Alright, and if I went to up 4, 1, 2, 3, 4, there's that. And so my line is the line that goes through those two. Let's see if I can't get this to... There's my shining white line right there. Okay? So that's the solution to equation 1, right? Now what about equation 2? Let's do the same thing again. Now for equation 2, I'm going to plug in 0 for y. I get 3x is equal to 3. So divide both sides by 3, I get x is equal to 1. Okay? And then if I do 0 for x, I get negative y is equal to 3. Divide both sides by negative 1, I get y is equal to negative 3. Okay? So 1, 0 is right here, and 0, negative 3, 1, 2, 3 is right here. So the line that goes through those is right here. Now where's the point of intersection? Notice it's right there. Okay? That means that the solution is 1, 0. Now we just got lucky here that 1, 0 was also a point that we plotted, and so we know it satisfies both equations. Sometimes we will have plot two lines and they intersect at a point that we didn't use, but we will still have to find the coordinates of that point. Okay, but that is the way that we would solve by graphing. The next method for solving systems of linear equations is the method of substitution. In this technique, what we're going to do is we're going to solve either of the equations for one variable in terms of the other. So we need to pick a variable, so we're going to solve for x in terms of y or y in terms of x. If one of the equations is already in this form, this is a good indication that substitution is going to be our best technique, and we can go ahead and skip this step and jump right into step 2. Step 2 is to then substitute the expression found in step 1 into the other equation. For example, if we had solved y equals something in terms of x, that means we can replace y in the other equation with that expression that depends on x. The result is an equation that has only one variable. If we have one equation with one unknown, we're back to a linear equation of one variable, which we can solve by just getting that variable by itself. So that means we can solve the resulting equation containing only one variable. Then we back substitute. We take that answer and plug it back into one of the original equations, or actually we could even plug it into the result of step 1 and simplify, thus giving us the value of the remaining variable. Okay? We always want to then check the proposed solution in both of the original equations, right? That's our check step to make sure that we have done everything correctly. So let's take a look at this example here. So, to solve by substitution, we're going to pick one of the equations and solve it for one of the variables. In this case, I'm going to pick the first equation because it's actually very easy to solve for y. All I have to do is move the 4x to the other side. So from equation 1, I have y is equal to 4 minus 4x. All I did was subtract 4x from both sides. Okay? Now substitute into equation 2. That is, take this and stick it in where there's a y right there. So I'll have 3x minus, in parentheses, 4 minus 4x is equal to 3. Notice how now we only have one unknown. We have the x. So I can now solve this for x by simplifying both sides. That means distribute the minus sign. So I have 3x minus 4 plus 4x, because minus 4 is minus 4, minus a minus 4x is plus 4x, equals 3. Let's combine like terms. So on the left hand side I'll have 7x minus 4 is equal to 3. Now to get the x by itself, I'll add 4 to both sides. I get 7x is equal to 7. Divide off the 7, I have x is equal to 1. Now we're not done, because we've only found one variable. To find the other variable, I'm going to plug back into right there. Right? Find y. That means y is equal to 4 minus 4 times 1, or 4 minus 4 equals 0. So the solution is 1 for x and 0 for y. And since we already know how to check that, I'm going to leave that to you to double check, but that is the final answer. Now let's look at this example, where again we're asked to solve by substitution. So this is the system we want to solve. Looking at this, my suggestion is that we're going to solve the first equation for x, because that's the easiest one to solve for, as a coefficient of 1, right? So let's solve equation 1 for x. That gives me x is equal to 5 plus 6y. And again, I get that by adding 6y to both sides. Now substitute into equation 2. All right, that gives me 3 times whatever x is. So that's 5 plus 6y minus 18y is equal to 6. Now we are going to solve this for y, so we begin by simplifying. If I distribute the 3, I get 15 plus 18y minus 18y is equal to 6. In simplifying both sides, here's what we end up with. Notice what happens. 18y minus 18y completely cancel out, and I'm left with 15 equals 6. uh-oh, the variables are gone. Now, do you remember what we do when we lose all of the variables? When we lose all of the variables, we end up with an either true statement or a false statement. If it's a true statement, then we'll say that there are infinitely many solutions. If it's a false statement, which we have here, that's false. Remember, that means that there is no solution. Okay? How is it possible for a linear system to have no solution? Well, if the two lines never intersect, meaning if the two lines are parallel, then you're not going to get an intersection point. So it is possible to have no solution, which is what we have here. The last technique that I want to show you for solving a linear system is something called the addition, or sometimes referred to as linear addition. The first step in using this technique for finding the solution to a system, is to make sure that it's in standard form. So let's rewrite the equations in ax plus by equals c form. That means get the variables on one side and the numbers on the other. Okay? Then what we're going to do is we'll do this for both equations. So we'll line up the x's, we line up the y's, and we line up the numbers, and our system will be all nice and organized. And once we do that, we're going to try to add them together. But we want to add them together in such a way that either the x's cancel out or the y's cancel out. Now, if the coefficients aren't just right, that's not going to happen. But we can multiply either equation or both equations by some number. Okay? Maybe the first equation by one number and the second equation by another number, but we can choose those numbers so that whenever we multiply them in, once we do that, we add them up, one of the variables will cancel out. Okay? So, if necessary, multiply either equation or both equations by some non-zero number so that the sum of the x coefficients or the sum of the y coefficients is 0. Once you do that, you add the equations in step 2, and the result, just as we saw in substitution, will be an equation of one variable. Okay, once you get that one variable, one equation, you solve it, and then just like we did before, we use back substitution. Okay, in either of the original equations to solve for the other variable. Okay, then we check the solution in both of the original equations just to check. Okay, so let's look at this example. First thing we got to do here is we need to get this in standard form. Okay, that is, I'm going to move the 2y to the other side here by adding 2y to both sides. I end up with 4x plus 2y is equal to 4. And I'm going to move this minus 3x to the other side by adding 3x to both sides. That gets the x's and y's all on one side. 3x minus y is equal to 3. Okay, now what I want to do is I want to add these things up. Now if I just added them right now, I'd have 7 x's, I'd have 1 y, and I'd have 7 on the other side. I don't cancel the variable. But notice what happens if I choose to multiply this by 2. Notice how this is a positive 2. If I were to multiply this by a negative 2, if I were to multiply this by a positive 2, this would become a negative 2 right here. And then when I added them up, 2 minus 2 gives me 0. Right? So what I'm going to do is I'm going to multiply equation 2 by a positive 2. Okay, so I end up with 4x plus 2y equals 4 is my first equation. My second equation, if I multiply this times 2, that means 2 times everything, and it was 6x minus 2y is equal to 6. Now add those equations up. Okay, if I add them, I get 10x, the y's cancel, I equal 10. Dividing both sides by 10 gives me an answer of x is equal to 1. Do you see how that works? Now I could very well have tried to cancel out the x's as well. I still get the same answer in the end, but if I try to do the x's, I could multiply, say, the first one by 3 and the second one by negative 4, and that'd become a 12 and a negative 12. All right, see how you can choose the values that you multiply by so that when you add them up, they cancel out. Now, how do I figure out the y? Well, I take this and plug it back into the original equations. Okay, so let's say I plug it into the second one. Find y. And I could very well plug it into one of these, but I'm going to plug it back into the first one. So I have negative y is equal to negative 3 times 1 plus 3. So there's negative y is equal to negative 3 plus 3. Negative y equals 0. Divide both sides by negative 1. I end up with y is equal to 0. So my answer is 1, 0. Now this was a modification, a slight modification of an earlier problem, so that's why we got the same answer. You're not always going to get this answer as a result, but we can plug this back in and check, and of course it will work. I'm going to save time by leaving that for you to do. In this example, this is a prime candidate for using the addition method, because when you look at it, you see that the y's will already cancel themselves out. So there's nothing I have to do in step 1 or step 2, right? I don't have to get it in standard form because it's already there, and I don't have to multiply anything in to get these things where they're canceled. So now I just add to both of these. I'll add both of these equations together. Those cancel out. I'll have 4x minus 2x gives me 2x. And I'll have that equals 4 plus 2, which is 6. Dividing both sides by 2 gives me x is equal to 3. Okay, now to find y, I'm going to plug that x equals 3 back into the original equation. So 4x plus 15 times 3. Oh, get that backwards. How about 4 times 3 plus 15y equals 4? Right, that's 12 plus 15y equals 4. Subtracting 12 from both sides gives me 15y is equal to negative 8. Dividing both sides by 15, I get y is negative 8 over 15. Okay? And so your final answer would be the point 3 comma negative 8/15. And that's your final answer. Now let us summarize the methods that we've talked about for finding the solutions to a linear system. We've talked about graphing, substitution, and addition. Now there are, like I said, advantages and disadvantages to each one of these techniques. Okay? The advantage to graphing is that you can see the solution. Now you can actually visualize what's going on with those two equations and where they intersect. Now the problem with graphing is that it's impossible to tell exactly where the solutions are. Okay? If the solutions aren't integers, if they're fractions, it's going to be very difficult. Say, for example, on that last problem that we did, we got a y equals negative 8/15. How hard is it going to be to figure out that that's where the two lines intersect? It's going to be virtually impossible. So, unless they're integer solutions, graphing is almost never the best technique, unless you just need to see what it looks like. But you're not going to find exact solutions using graphing. Now, substitution, both substitution and addition have the advantages of giving exact solutions. Okay? Now, the best time to use substitution is if a variable is on one side by itself already. Okay? Now, the difficulty here, the disadvantage, is that solutions can often not, well, you don't get to see the solutions, but it also sometimes introduces extra work with fractions when no variable has a coefficient of 1 or negative 1. Right? You can imagine that if you had to solve for a variable and that variable happened to have a coefficient that wasn't 1, you're going to have to divide off that coefficient, and so very often you may end up with fractions, and that can make this a lot messier. Okay? So addition doesn't have that disadvantage, but it does have the disadvantage that solutions cannot be seen. And also I want to go back and take one quick look at the different types of answers that you may be able to get out of a linear system. Right, we've talked about one example, that is, we get an ordered pair. We've also talked about a second example where you might get no solution. And of course, there's the third example, that there are infinitely many solutions. Now, you can look at this graphically and see what we're talking about. Right? If I start with a Cartesian coordinate system, if I could draw straight lines, I would. How about I just cheat and do it this way? Alright, so draw a line. If there's a second line, boom, if there's an intersection point, that's what's going to happen. Now, what are other options? What are other ways this could happen? These lines go other different directions, but still intersect. Now, it's possible then to get one that doesn't intersect. Let's try a better picture. Let's do this one. Okay. Now, what if they don't intersect? That means the two lines are parallel. This is what happens when you have no solution. They don't ever intersect. And last of all, if you have two lines, but they happen to be the exact same line twice. Right? How many points do those things overlap? Well, they overlap on all of their points, right? So that's when you have infinitely many solutions. Okay? When they're the same line. This is when they're parallel. And this is any type of intersecting lines. So you could get exactly one ordered pair solution, you can get no solution, and you can get infinitely many solutions. Let's do one last example with a word problem involved and see how we might use the techniques we've learned in this section to answer some word problems. We're given that at a price of P dollars per ticket, the number of tickets that a rock concert the number of tickets to a rock concert that can be sold is given by the demand model. N is equal to negative 25p plus 7,800. At a price of P dollars per ticket, the number of tickets that the concert promoters are willing to make available is given by the supply model. N is equal to P plus 6,000. How many tickets can be sold and supplied for $50 a ticket? Now that's easy enough. All they're asking is how many can be supplied, how many can be sold if P is 50. So to answer that question, you just got to plug in P is equal to 50. So the number for the demand would be N is equal to negative 25 times 50 plus 7,800, which gives me negative 25 times 50 is negative 1,250. Actually, let me write it over here. Negative 1,250 plus 7,800. So if I add those together, I end up with 6,550. All right. The demand, the amount that I could sell, is 6,550 tickets. But how many at that price is the concert promoters willing to make available? That's the supply. I would take 5 times 50 plus 6,000. Okay, that gives me 250 plus 6,000, which is 6,250 tickets. Okay, which means I can't meet my demand. There is more demand than are tickets available. The question then is, when do supply and demand meet for these particular models? That is, when will the supply and the demand be equal? That's the optimal number of tickets to sell and to supply. We need to find that price point that makes those equal. How do we do that? Well, we have a 2x2 system, right? We have two equations. N is equal to negative 25p plus 7,800. And we have N is equal to 5p plus 6,000. So let's solve this. Now we got three techniques. One, we could graph. We're going to opt out of that almost every time. Two, we can do substitution. Substitution is good when you've already solved for a variable, which in this case we have. Notice how the first equation, actually both equations, have been solved for N. So let's take the first equation and substitute it into the second equation. Right? That is, I have N is equal to negative 25p plus 7,800. Let's plug this right-hand side in for N right there. Replace N in the other equation. So by substitution, I will have, replacing this N with what it's equal to in the other equation, I have negative 25p plus 7,800 is equal to 5p plus 6,000. Okay, so let's subtract 5p from both sides. I have negative 30p. Let's subtract 7,800 from both sides. Gives me negative 1,800 on the right. If I divide both sides by negative 30, of course, the negatives will cancel. I can cancel one of the zeros because that's 10 comes out of both of those. That's completely gone. I get P is equal to 180 divided by 3, which is 60. Okay, and what does P represent? $60, right? That's the price. Now, I can still find what the supply and demand for the number of tickets are, but the first question was, what's the ticket price? There's the ticket price. So how many tickets will we have? How many will be sold? To figure that out, plug it back into one of the original equations. That is, take N is equal to, say, 5 times 60 plus 6,000. Right, that gives me 5 times 60. 60 is 300 plus 6,000, or 6,300 tickets would be sold at that price. All we do is plug the 60 back in. All right? Okay, that's the end of section 3.1.